x plus 0. Some people just write it's the 0 vector is just equal to 0. But I wanted to write it this way so you can see that essentially I have 0 in each one of these components, for each one of my coefficients of my polynomial. Or I could just write the 0 vector is equal to 0, but it's the 0 polynomial, not the 0 number, right? So it's a function that is the 0 polynomial. It's the 0 vector here. So if I were to add 4x squared plus, that's a really bad x squared here, plus 7x plus 2 to the 0 vector, 0x squared plus 0x plus 0, I end up with 4x squared plus 7x plus 2. Okay. And I don't have enough space to squeeze in negative u, so let me erase something here. So suppose suppose I want to look at property number 6, right? Property 6. So so I have u. Let's suppose u is equal to 2x squared minus 7x plus 4. I'm using a lot of 7s today. So negative u would be equal to negative 2x squared plus 7x minus 4, right? Because what happens when I do u plus negative u, right? If it's standard addition and scalar multiplication, right? When I add these two guys together, I get 0x squared plus 0x plus 0, which is our 0 vector that we have over here. That's what we define it to be. Okay. Again, I can go through properties 7, 8, 9, and 10 and show that those hold, right? As long as we have standard addition and scalar multiplication. But I think that's enough for us to be able to kind of get the idea, right? If you look on the PowerPoint, you notice that I have other vector spaces here that you can look at. And let me just I'll just put their name down. I'm not going to do any examples, but that's two more that are here. Of course, you have the complex numbers. So I have the complex numbers. With standard addition and scalar multiplication. So let me not write that with standard addition and scalar multiplication. I'm going to say I have the complex numbers are going to be a vector space if we're dealing with standard addition and scalar multiplication that we're used to. Okay. We have the functions c negative infinity to infinity. So this is different from the complex numbers. This means all continuous functions on the interval from negative infinity to positive infinity. Okay. And we're assuming again standard addition and scalar multiplication, right? So how we add functions together, how we multiply functions by a scalar. Okay, that would be a vector space. And then we have another one which was C. Here I have brackets A to B. And there's multiple versions of this, so you can have half open intervals. Here, this one's a closed interval from A to B, but we can have a half open interval from A to B, either on the left side or the right side. And this is, again, this is going to be continuous functions on interval from A to B. All of these are examples of vector spaces. Here, again, I'm assuming standard addition and scalar multiplication. When we talk about vector spaces, we always have to talk about the set of objects. My set of objects here is going to be the complex numbers. Then we have to talk about how we operate on those numbers with addition and scalar multiplication, right? And I'm assuming standard addition and scalar multiplication for the complex numbers, the continuous functions on the interval from negative infinity to infinity, and then the continuous functions on the interval from A to B. Okay. Let's look at some of those guys. Let's look at some other examples of vector spaces where we have that are more interesting. We're going to get to non-standard addition and scalar multiplication soon, but let's do one of the simplest vector spaces there is. Erase this. I don't want to erase this stuff over here. That's a bad thing about having a small board, right? Sometimes you want to erase stuff. I guess I could erase it and tell you guys to refer to your the PowerPoints, and I might do that. If I start to feel like I don't have enough space to really stretch out and write whatever I want to write. But right now, I'll leave it up there. So we're going to talk about the zero vector space, which is the smallest vector space that we have. Zero vector space. So let V consist of a single object, which we denote as the zero vector. And define standard addition and scalar multiplication by 1, 0 plus the 0, 0 plus 0 is equal to 0. Or I should say the zero vector plus the zero vector is equal to the zero vector. Yeah. 2. Here I have k times 0, where k is a scalar. K times the zero vector is equal to the zero vector. Okay. So in this case, k is a scalar. Now, here we don't say what V is, right? So V could be any vector space, right? Well, we don't define how V is structured. So V could be a matrix of size 2 by 2 or 3 by 3 or 4 by 4 or 5 by 5. It could be a polynomial vector space, 0x squared, 0x plus 0. Essentially, we're essentially looking at the smallest possible vector space you can have inside of a mathematical object. And this is called the zero vector space. And the zero vector space is the smallest vector space within any vector space. It's the smallest vector space within any vector space. Essentially, the zero vector space is a subspace within any vector space. It's the smallest possible vector space you can have within another vector space. Okay, that is the zero vector space. Or you can think about the zero vector space as a vector space on its own. So you can think about the zero vector space as being the smallest vector space within a space, or the vector space, zero vector space being just a vector space all by itself. Okay. And if you want to, you can go through all of these properties, right? But there's only one object in here, so U and V will always be 0, okay? And W will be the zero vector. And so everywhere you see a U and V and W, we'll just place it with the zero vector. Negative U would be the zero vector, okay? So everything you would, and you can go through all of these properties and see that all these properties hold. Okay. And then we have properties of 0. So if V is a vector space, the following are true. And these are properties of things which deal with 0. The first property is that 0 times U. So the number 0, when you do scalar multiplication with U, is equal to the zero vector. That's the first property. So if you do scalar multiplication of the zero vector if you scalar multiplication of 0 with a vector in the vector space U, then it's always equal to the zero vector. Okay. Now, before I keep going, right, these properties have nothing to do with this zero vector space idea that I have up there. But this is the zero vector space is the smallest vector space. What I'm doing here is I'm talking about if I have any vector space in these following properties are going to be true. 0 times u is going to be equal to the zero vector. 2, k, which is another scalar, times the zero vector is equal to the zero vector. That's always true. 3, here, if k times u is equal to the zero vector, then either k equals 0, okay, so either the scalar is equal to 0, or u is equal to the zero vector. Those are the only two options. If this equation is true, if k times u is equal to the zero vector, then either k is equal to 0 or u is equal to the zero vector. One of these guys has to be true, or maybe both of them are true, right? But when we say or, this is the inclusive or, not the exclusive or. All right, very, very good. And this is one of those properties that we're going to actually use later on, in just a second. So here are examples of vector spaces with non-standard addition and scalar multiplication. Okay. Now, when I say non-standard addition and scalar multiplication, it's essentially I make up the addition and I make up the scalar multiplication, right? I define how I think about addition, and I define how I think about scalar multiplication. Okay. Here's the first one. So the vector space V I might just say V from now on and just assume that I'm talking about a vector space unless I tell you otherwise. It's the set of all real number pairs one comma y, okay, with addition and scalar multiplication I'll say it like this, with addition and my addition is going to be this, 1 comma y1 plus 1 comma y2 is equal to 1 comma y1 plus y2. Now here, y represents any real number. I should say that. This 1 is always going to be the same for the first component. This y represents any real number I want it to be. Okay. When I add two pair of numbers that have the form of 1 in the first component and any real number in the second component, when I add them together, I get 1 in the first component and then the addition of those real numbers in the second component. And scalar multiplication, what did I use? Did I use K? It doesn't really matter what you call it. I use K, you can use C, you can use D, you can use R, K of 1 comma Y, right? So if I multiply a scalar times a pair, real number pair in this vector space, right? I get 1 comma KY. Okay. So the k does not get multiplied to the 1, it just gets multiplied times the ky. Okay. And now the question is, okay, I want to be able to, this is a vector space. I could, if I wanted to, I can go through all those properties and show you that it is. And I can show you that if I add two vectors in that set together, right? Two vectors with this addition, I end up with a vector that has the same form. One in the first component, any real number in the second. Scalar multiplication is the same thing. Essentially, I define my scalar addition and my addition and scalar multiplication so 1 and 2 are satisfied. It doesn't matter in which order I add them together. It doesn't matter if I add another vector or not. I get the same thing. Okay, as long as I go with this addition and scalar multiplication. What I'll do to kind of help you to understand this a little bit better is that I'm going to change this. You see this plus right here? Now, this plus represents the way I do addition, but this plus is just the regular addition that we're used to. Okay, so y1 plus y2 is the regular addition that we're used to. This plus here represents the addition that I just defined. So what I did is I'll change this to, let's pick a different color for this. Let's use red. I use red here to represent that I'm using a new type of addition. And I'll put a dot here in between the k to represent I'm doing a new type of scalar multiplication. This is regular multiplication that we're used to. This is scalar multiplication. Eventually, you'll get used to it. Whenever you have two vectors and you add them together, you're going to be using whatever addition that you have set aside. All right, let's do a couple examples to show you guys what's going on. I'll talk about the zero vector and negative u. Okay. Suppose I have this. Let's suppose I have u is equal to 1, 4, and I'll say that b is equal to 1, 6, okay? Then, in this case, u plus b, right, that's going to be 1, 4, 1, 6. I'm going to add them together. Right? So I have a vector in my vector space V has to have the form that I have right there, 1 comma, whatever real number I have there. When I add these guys together, I get 1 comma 4 plus 6 or 1 comma 10, right? Okay. And if I do, let's say, 3 times u, dot there, just kind of remind myself that this is a different type of scalar multiplication. Let's just say it means 3, 1, 4 times here. When I do this, this is the same thing as 1 comma 3 times 4. So this is regular multiplication, so I get 112. Okay. Which has the same form that I have here, right? So all my vector space pairs has to have the form 1 comma any real number. What is the zero vector? What is the zero vector in this case? Well, if you think about it, the zero vector should be 1 comma 0. 1 comma 0. Why is it 1 comma 0? Because if I take another vector, let's say 1, 6, add it to 1 comma 0. Okay. What do I get? I end up with 1 comma 6. Okay. So there's my zero vector. And what is my negative u? Right. So if I suppose this is my u, what would negative u be? Negative u. If I had this to be my u, negative u would be. What do you guys think? Some of you guys got it, right? It's going to be 1 comma negative 4, right? 1 comma negative 4. Why? Right? Remember, this is my zero vector. This is my zero vector, okay? So when I do u plus negative u, oh, I got to use a different. Okay. I get 1, 4 plus 1, negative 4, which is equal to 1, 0. Squeezed it in there. Pretty tight there. 1, 4 plus 1, negative 4. Oh, yep, you guys got me. 1, 4 plus 1, negative 4, I get 1, 0, which is my 0 vector that I have here. I know that seems a little bit weird, like that seems kind of arbitrary, but this is kind of what we're doing, right? My negative u is 1, negative 4, right? And some of you guys want to say this is negative 1, negative 4, but that's not the case, right? If it was negative 1, negative 4, then this vector would not be in this set. Because negative 1 cannot, if it's in this vector, if it's in this set vector space V, then the first component has to be a 1. It cannot be a negative 1. Okay. All right. Let's look at another one. Come over here. All right. Yeah. Let's do the next one I have here. This one's an interesting one as well. So V is the set of all positive numbers. It is a vector space. When I say it's a set of all positive numbers, all positive real numbers. What's a positive complex number anyway, right? What is that? All positive real numbers with addition.